Over the last decade, Indian Railways has aggressively strung thousands of miles of overhead wires across its main commuter and heavy freight lines. The vast majority of the network now runs entirely on electricity. If you travel out to remote branch lines or up into the steep hill routes, those electric wires disappear. You physically cannot thread heavy electrical gantries through tight mountain passes. Building the infrastructure across these rugged terrains is often impossible, and in heritage zones, massive steel poles ruin the historical landscape. Because of these geographical limits, roughly 10% of the Indian rail network is stranded. To move people through these regions, the railway has to burn fossil fuels. Eliminating that final fraction of diesel engines requires a completely different approach. That brings us to July 2026 and the launch of an experimental train in Haraya called the Namo Green Rail. This formation is massive. While European hydrogen trains typically run as small 2- or 3-car sets, this pilot project is a 10-coach formation designed to carry up to 2,600 passengers at a time. Getting a train of this size to run on hydrogen carries a 112 crore rupee price tag, roughly $13 million, just to get this single pilot train and its immediate support infrastructure functioning. Which raises a critical question. Is paying 112 crore rupees for a single train a practical way to replace the diesel engine, or is this simply an expensive science experiment? To understand where that money went, we have to look closely at the hardware. They didn't build a new train from scratch. Engineers took an existing diesel train, a standard DEMU rake, and spent 70 crore rupees to hollow out the propulsion system and retrofit it. In place of the diesel engine, they installed a 1,200 kilowatt fuel cell system. The mechanics rely on basic chemistry. The system takes hydrogen from onboard storage cylinders, mixes that hydrogen with atmospheric oxygen inside the fuel cell, and forces a chemical reaction. That reaction yields two things. The first is electricity, which is sent down to power the wheels. The second is the physical byproduct of combining hydrogen and oxygen, pure water vapor. There are no localized greenhouse gas emissions. Instead of thick, black diesel smoke pouring out of the engine, the only exhaust leaving this train is dripping water. The true challenge of hydrogen transit lies beyond the vehicle. Success depends on the complex logistics of producing, compressing, and storing the fuel itself. The remaining 40+ crore rupees of the budget was spent entirely on the ground at Jin Station, building a dedicated support ecosystem from scratch. This map illustrates the physical footprint required to support just this one train. To make it work, the railway built a 1-megawatt green hydrogen production plant right on site, along with heavy-duty compression systems and storage tanks capable of holding 3,000 kilograms of fuel. With the train and the fuel ready, they placed it on the Jin-Sonipat section. It's an 89-kilometer route with 14 stations. This is an everyday, gritty commuter grind. By dropping the train onto a working passenger route, engineers force the technology out of the laboratory. They can measure exactly how fast the components wear down, what the real-world fuel consumption looks like under heavy passenger loads, and how long it actually takes to safely refuel those cylinders. The Jin-Sonipat route serves as a grueling stress test, proving whether hydrogen logistics can survive the daily friction of Indian passenger transit. If the train survives this commuter stress test, the Ministry of Railways plans to trigger the next phase of its strategy, an initiative called Hydrogen for Heritage. This chart breaks down the proposed 2,800 crore rupee budget for that rollout. The plan involves building 35 specific hydrogen trains at an estimated 80 crore rupees each, alongside 35 separate fueling infrastructures, costing roughly 70 crore rupees per route. Those 35 trains are targeted at pristine, unelectrifiable environments like the Darjeeling Himalayan Railway, where century-old coal and diesel engines currently pump heavy black smoke over fragile mountain hillsides. They are also earmarked for routes like the Nilgiri Mountain Railway. By swapping diesel for hydrogen, the railway removes industrial pollution from these highly sensitive ecosystems entirely. The government is accepting severe upfront infrastructure costs in exchange for permanent zero-emission transit in ecological zones that cannot be protected any other way. Hydrogen operates as a highly specialized, expensive weapon. It serves a single purpose: eliminating the diesel engine in the exact corners of the network where overhead wires are impossible to build.